the recording. Okay. Thank you for listening. I'm happy to have a chance of sharing with you several of my pet peeves, and it's a bit of a misfortune that I come before Paul's presentation, but if you were here and heard it yesterday, maybe you can remember it. Otherwise, you can remember this tomorrow. But the reason why I came up with this is mostly the fact that there's been a lot of talk about trusting and trusting framework, and that's fine. But then my question has been there, okay, but how do you define your base of trust? So we are starting to talk about confidence. How confident am I that something that I'm setting as a sort of foundation of my safety claim will work or not? And just for the sake of having one or two pictures, I came up with this. Probably you are going to be somewhere in the middle. And what I hope that I can provide with this is at least my perspective of how to do some sort of self-assessment. I mean, this is talking about qualification where you go to a real assessor and try to convince the assessor that you're doing fine. But first of all, you have to convince yourself. So I've chosen, because that's also what I deal with mostly, to look at these three angles. Usually when you do a qualification, you have to talk about, well, there's a bunch of more formal perspective, which Nicole has been talking about, so I will not get into that much. But you still have to talk about safety analysis and some sort of validation or testing, which is both static and at runtime. You have different perspectives. And you also have different methodologies to look at it. You can inspect the code, you can make assumptions, you can analyze it. However, in reality, when we're talking about qualification from an engineering perspective, what we're doing is a measurement, and every measurement has a sort of certain error. I mean, if you're claiming that your measurement has no error, well, we already have a sort of problem there. So let's start with making this admission that there is going to be something that you will make a mistake, or you will forget it, or for whatever reason, it will not be perfect. So what does it mean that I have achieved a qualification, and how much will that qualification survive to different type of errors or mishandling that might occur? There are various parameters that affect it. You have correctness, like am I saying something correct, valid? Did I forget something? And these aspects, they are affected by the targets over which I'm performing this analysis. The simpler the target, the easier it is that what I'm doing is correct, or that I have enough time, enough allocated bandwidth to perform it well. Again, I'm not saying anything particularly new, but you cannot treat all the components as equal, because they're not. So first of all, there should be this sort of assessment of complexity of how difficult is a component to treat. Is mostly I'm looking inside the Linux kernel, because I think it's the okay. We have a sort of herd of elephants in the room by now, but we have said so many times that we have the elephant in the room, which is the Linux kernel. So let's start from the top, perhaps, which is the easiest part to look at. So you have some components which are mostly linear. They have some input, they have some output. They might even be complex per se, like crypto function. Crypto function is not something that I would approach happily, but still, it's something that you put a guy with mathematical experience on it, and he will tell you that this works, this doesn't. But then starts the fun, where you have components which have internal states, And then you have input vectors, output vectors, and you have to start to consider the fact that you might have omitted some of the possible configuration that are relevant, and you do not necessarily know what will happen in the field. And finally, we get to the main body of the elephant, where you have components with much more states, which interact with other ones, which might have even more states. And then it really starts to become a matter of being able to prove that you have even considered all the possible scenarios. So I know that one common practice in the functional safety field is to say, well, don't worry, we will do a safety analysis, we will analyze the code, we will produce test cases. And I'm like, come on, this is some code that has been written by some top engineers over decades, and you're claiming that you can get a bunch of guys, usually less, with less time, and that they will produce an analysis, good enough analysis. Maybe they don't even have the specific knowledge because they've been just hired for that job. So how realistic is the outcome that might be produced by this? Other approaches to look at cyclomatic complexity, static code analysis. So you have all these parameters which are typical tools of functional safety analysis. But again, how well do they fit to the Linux kernel? In some scenarios, you might have relatively simple functions, which on the other hand interact in a very complex way, involving also hardware components which have additional states, and you might not even be fully aware of them because they might even be partially living inside some firmware that you might not even know how it works. So again, the fact that something looks simple doesn't mean that it is. And static code analysis, I think if anything else, if you run static code analysis on the Linux kernel code, it's proof that you shouldn't rely much on that because it will produce a gazillion of findings. But then if you look at it, first question you would ask yourself is, why didn't it explode yet? The answer is because most likely those are not bugs, they're not errors. Then we switch to the live part of the verification. You can run code coverage, but even there, the fact that you have passed once over a certain function doesn't mean that you have covered the possible inputs that that function might receive, all the possible scenarios. You have some functions which are exerted a lot. So perhaps they are, if you have a high frequency, not only code coverage, but if you pass over it multiple times, perhaps you can make a good argument. But if you are not even tracking that aspect, it doesn't tell you much. Then the other option is to have a fault injection. That's also a common practice, but even there, at least if you rely on upstream components, most of those upstream components, if they support fault injection at all, they support it on very specific scenarios, which are not usually the only ones that we care about here. So the fact that you run fault injection doesn't mean that you've done all that was probably necessary. And this is how we see, again, trust. How complexity can affect the amount of trust I can put in a certain qualification activity. Really, what's my strategy? Am I ready? Hopefully you're not putting your head in the sand. So here a coworker told me that in reality what I'm talking about is architecture, but that seems to be another one of those taboo words. So I'm not saying architecture, but really the question is, how well do you understand the overall system architecture of each components that you put as a pillar of your safety strategy? And I want to stress the fact that I'm talking about really understanding at the code level, not just the block diagram, because the block diagram, then you're just shifted the question on whoever provided you the block diagram, how well did this person understand it? Because the Linux kernel doesn't produce architectural diagrams. And that's, again, maybe the 4 times you see it today, but really, if you don't understand the component, how can you perform a safety analysis of it?
Yes.
These are, I think, the basic questions one should ask. In particular, one part that I find lacking often is the last one about negative testing, because in many cases, the validation or qualification is performed in a way where I'm just showing that I believe something works, and perhaps I'm even able to show that it does work as intended. But then I'm kind of assuming that it will never be tested for real. In case there is an interference, it might put me completely off balance because I have no evidence that the system is going to survive that interference if I do not have negative testing. And that's what I call empirical verification. It's like if I'm selling you a bulletproof vest, you probably want to see me wearing it and take a bullet. Then perhaps you buy. So we come to mitigations. There are various aspects. Again, the comprehensiveness is one that is probably more obvious, but the efficacy, how demonstrable is it that it works, that goes back to the negative testing. If I cannot prove that my mitigation works, how good is it? Do I want the customer to find out? And even if I have monitors, then I have to be careful that they cannot be affected by the same sort of interference. Otherwise, again, my claim is mostly void. So I need to figure out what are the weakest part of my, like we call it, safety chain, even if usually one talks about security. So one argumentation that usually comes up after I present the previous arguments is, oh, but I'm going to test it. Okay, but then we are back to the same problem of complexity. If I do a black box testing, how can I prove that the testing is good enough? I might go on for days doing testing and never test the correct conditions because I do not know what are the internal states. And how can I express the degree of completeness? Did I test 95% or 5%? Yeah, so survival bias is probably the best way to describe it. Like, so far it went well, so it must work. Crossing fingers. And then usually, here I'm really listing out all the objections I've heard so far during the last 3 years. Usually the answer I get is, oh, but we're going to do stress testing. But again, if you do not know how your system behaves, how do you know that you're stress testing the right things? And even if you manage to expose bugs, once you fix them or when you think you have fixed them, how can you prove that the fix was really effective if it's hard to reproduce because you just run it 20 hours and something came out? If you run it again 20 hours, will it come out again or not? And does it mean that if it doesn't come out after 20 hours, maybe you have to stretch it to 30? So there is a variety of antipatterns that really affect complexity, the confidence. The simpler the component is, the easier it is to make any claim about it because you have less to prove about your understanding of it. And from my perspective, whenever I see someone who claims that, oh, but we can easily test for safety a complex component, then I'm starting to wonder how well this person understands that component.
Will it then include the effect of testing?
Don't know what you don't know.
I didn't.
Dunning-Kruger effect. You don't know what you
Yes,
don't know.
yes,
Yeah.
yeah. And then the other common answer is, oh, but I can simplify, I have this model. Again, the fact that it looks nice on PowerPoint doesn't mean that it matches the ugly reality of the system. Or also, like, how did you decide that because testing was enough? Did you run out of money? Because if that's the answer, then perhaps you should find a different strategy. Here I'm kind of repeating the same point I made earlier, like reproducibility, I think, is fundamental, because if I have a bug and I can reproduce it reliably, then I can root cause it, I can fix it for real, I can just justify my claim that I fix it. If I cannot do that, then it's always a question of did I just hide it better? Sometimes it might be enough, but if I cannot even prove how well I hid it, then no. So how can we try to increase the trust that what we're doing is efficient? I usually start from the expectations. So if my expectation is that I will do the qualification and it will all go smoothly and happily, and it will prove that whatever I did was already correct, that perhaps is not such a it doesn't give confidence, because then the following question is, but what are you going to do if you find that you have a problem? Are you just hoping that you will not have it? And are you following the guiding principle of the standard? Because if we are trying to avoid standards because they are too expensive, too difficult to cope with, then that's again not a good sign. So really, do I have the strategy? Do I have the ability of recovering from a failure in my assumption? So if I started assuming that a certain component was safe and it turns out that it was not, can I cope with that? Another way to look at it is, if I have methods to detect and report safety relevant failures, that to me is already a good indication of the fact that I'm aware of the fact that there might be failures, there will be failures, and that I'm prepared to deal with them. Evidence of the fact that this detection works is also useful to increase confidence, which again means that I probably have ability of performing negative testing, because then I can prove that the whole chain works. Because the alternative is I'm claiming that everything is error-free, but then I have to prove that, and it's going to be an interesting show. So these are a few ideas. I'm not claiming that they are complete, but if I use simpler components and probably try to use different approaches to certain complex components, and possibly have a detection and reporting, that's a way to have also self-measure of how well my safety strategy is working. Using safety simpler components means, amongst other aspects, the fact that it will be also more maintainable over time. Like, one of the problems that usually I see is the fact that in most cases the effort might be manageable once, but then it doesn't survive rebasing. So at that point you might see some software which is 2-3 years old before even getting to a product, because it was frozen in time and that's it. coming to component complexity, the nice thing about Linux is that there is variety. So very often you actually have multiple components which are alternative to each other, and choosing the fanciest one is not always the best choice from safety, quite opposite usually. So the real question there is, what are the motivations that led you to choose a certain component, and can you choose a simpler one that still fulfills your requirements? And well, again, if you're not testing it, assume that it is broken. So do not make a safety story based on that, especially the negative testing. And well, I managed to finish in time. If you have objections.
No objections, no disagreements with the points you're raising. It's just a question of finding our path through them. In the sense that we need to figure out how to change the landscape. And this is, so I think we're seeing ideas coming out here, and that's good. But I think these are things to cross-check ourselves against.
I'm quite happy with the work that we've been doing with Alessandro, trying to identify what are the components that you really cannot do without.
Yep, that's all part of pulling this together.
And then the next question could be, okay, can we identify pairs or triplets or whatever alternatives, and make a comparative analysis of complexity versus features, so that at least we could offer a sort of menu to people who want to create their system.
I'll start down by saying what can go wrong in the component that you use with the build models.
I have a comment. So one of the earlier slides were about, what is the quality of the safety analysis for a complex component, right? Because we were saying like safety analysis are done on like conceptual blocks. Right? Yes. So yeah. You say these are done on conceptual blocks, but then it is quite easy that we miss, something is missed, right?
Not something, but even some configuration. Like you might look at all of the states, but did you really understand what are the possible?
I understand, but there is one thing that we also need to consider, that, or at least this is my experience, for along my career. So I've seen many projects in functional safety that claim to be safety compliant, where there is there are requirements and a very nice architectural diagram that is analyzed by functional safety expert and architects, right? And then it's say, okay, now we have broken down, the low-level requirements, we've done the safety analysis, and everything is passed on to developers that are thousands of miles away. And then, you don't know what happens, like from an implementation, if, the implementation itself actually matches the hypothetical architecture, right? And whereas here, at least the good thing is that we are starting from a pre-existing software, and we analyze it by trying to extrapolate the architecture from the software. So this is.
I don't see that. I mean, I'm not saying that we shouldn't use
No,
Linux.
no, I'm saying no. I would just consider that to some extent this is it's not like what I'm going to say is that if I compare what we're trying to do versus a traditional project that theoretically follow the V model with all the checkboxes, right? It's my gut feeling is that it's not the level of confidence with respect to the goodness of the analysis.
So the quality that you're describing is not safety, it's quality. I mean, if your requirements of much implementation, you have other kinds of problems where, even worse, I shouldn't say worse, but they're more basic than safety. I shouldn't say worse, they're more basic than safety. If you ask for X and you get the opposite of X, your system is, it's unpredictable anyway.
Mhm.
Yeah,
This is not really a system. it deserves a safety analysis.
But I think the real key is that, so I think we often use the term safety analysis to refer to two different things. One of which is what you were describing, which is I need to understand my component in complete detail so that I can understand the ways in which it can go wrong. The other one is I need to understand the system and the role that these different components have in it, which is different. And you're right, for one, yes, you're absolutely right. You cannot avoid having that deep engagement with the thing. But the other one, you're not trying to understand everything about that individual component. You're not trying to do I think somebody recently accused us of looking at the subatomic particle level of things. They were just interested in organic chemistry. But you're right, sometimes that is necessary. But if you're dealing with something above that level of, the subatomic level, the quarks don't matter so much. Now, that doesn't mean that the quarks can't come along and absolutely turn over your expectations. But that's the point, isn't it? Is that as long as you're allowing for that, as long as you're allowing for the wild and improbable bit in your overall system analysis and system design, you don't necessarily need to have that understanding down to the level.
My view is why choose when you can have both? But the point is if you first start from the low level part, then you're sure that you've covered all the parts that you care about. And then from high level, you can confidently look at the bigger picture because you know that you have already taken care of all the smaller one. There is no surprise. In some cases, when I see this top-down analysis where you have all the wishes, like, oh, I want to have this fancy component, that, and that. Yeah, but then there's a price to pay that you're just postponing, which is eventually you get to the kernel and you figure out that, oh, I have to make all of this stuff work and I have to rely on all of these components, because otherwise everything above collapses. But if you start from the foundation, then you know where you can put.
But we're not starting with a system that doesn't work. We're
But-
starting with a system that works in millions of computers already. So in a sense, the behavior is something that we already have a degree of confidence about. What we're interested in are the edge cases that we haven't thought about. And you're right, those are the ones we want to expose for our specific use of it, particularly if that differs from your wider use.
But without understanding the full behavior, you cannot understand the
You're
edge
right,
case.
yeah.
Maybe Daniel wants to bring in another
Yeah, I
perspective,
want just to,
raising the hand.
we are talking about a complex system right now. For example, and for some reason, we need to go to that direction. It's not that we don't think that simple systems wouldn't be better and easier.
Complex component, the system
Yeah.
will be.
A system even more complex.
My
But
point is,
let's get a
if you
complex
have
component.
alternatives, why go for the complex one?
Yeah, but
At least
we are
justify it.
assuming we don't have an alternative. So that's kind of a scenario where we are going with very complex functions that will need complex components. That's what we are postulating. That's why we are going for Linux. If we could solve things with a very simple microcontroller or micro functions, everything simple, and we probably don't need something like that. But what I'm supposing is we want to enable Linux because we want to also enable complex functionality. And therefore we need a complex system or complex component. So my point is a little bit different. If we assume that we are dealing with a complex component, then your reduction strategy will not work because you cannot analyze a complex system, complex dynamic system by reducing it to smaller parts and understanding them. We know that from biology. So we have to think of alternative methods of getting confidence that do not rely only on knowing how the micro parts work. Knowing how the micro parts work might be part of the job, but we have to get to ways of looking at it without understanding how those micro parts work individually. We still have to get some level of confidence and be able to put a number on that, because else we will not go further on complex functions for that.
Okay.
I would like to offer an alternative view.
Yeah.
First of all, I love that simplicity is the king. I mean, it's very French from. So from Little Prince, it says somewhere that something is beautiful where there is nothing to remove, and I fully subscribe to that. And but if you start without logic, I mean, we would end up in a microcam, right?
No.
And that's the real, in my opinion, that's a risk if you start such kind of analysis. You will end up in a microkernel, having services running your servers, and then you end up in a more controllable, more predictable system. And in my opinion, Linux brings a unique other perspective to a safety critical system, which is performance.
Well, but my point is, you have to understand the price you're paying. So if you do not know that, then you do not know if it's worth it. Yep.
And I guess one point is also, it's not I mean, there are complex components, as you say, and they have a lot of states, a lot of inputs out of what could be there. And I get the key message which you bring in is like a safety analysis on such a thing is super, super complex, even more complex than the things are there. But you also need to kind of like, do I need to have this on this component? Do I really need this component? And it could, I mean, it would be just a logical thing to say, I have this super complex component over there. I want to make use of it. I don't understand it, and I want to use it for a safety critical thing. And then it's better to say, I'm better not using it than inventing something. It's not about the Linux system or antipatterns. It's like you put here for as a Linux and an armor. I mean, what would be worse is like, you say, okay, as a Linux is a better solution, but I don't know how to configure it. So do a wrong configuration. It could cause more harm than saying I use AppArmor as a more simpler one, but I have a better confidence in when I'm using it. And to a very practical example, a person approached me for like there was this Windows 10 October end of life thingy, and they approached me at Embedded World and just said like, oh, we have a radiation measurement detection, something like radiation detection device, which need to survive the next 20 years in field. And we are super concerned. We want to go for Linux, but we have to update. There's all these packages and all these kind of things, and we don't know how to do this for the next 20 years. And said, what is this device doing? Well, it sends data every 15 minutes, what the radiation status of this entity or what this is. And I wanted, so it's interacting with a sensor. Yes. So your system is a radiation sensor and a gateway to the internet. And you say, you want to build it with a full-blown Linux? You could go for an artist like Zephyr or anything else, because you just need a sensor. Anything else, why overcomplicating whatever you're doing just because it looks more fancy or it's just like the first thing you thought about? I think that's what you're also telling here is like, can I go to what is the fit I need? Where do I need the analysis and where does it stop?
Yeah, the top-down part, it really is problematic because you tend to not realize the cost that you are going to incur till the last moment. So at least within ELISA, what I hope is that we can make this cost more evident so that people from the beginning understand what they're getting themselves into if they choose a certain set of components.
Yeah. And what we also need to say there, and then we have the question in the back, it doesn't mean that because one person is not able to handle a certain complex unit, it doesn't mean another person can, like say, if you are a maintainer of the component, you will have a completely different understanding than the one who is a user. So, and I want to get the comment from back.
That here is that the traditional method of safety analysis, as we look in Evo 2662 and other standards, have been developed in the code. And that has also, I mean, it is applicable to a very wide variety of use cases, of course. But here we are dealing with a piece of software that has been proven in the field for quite a long period of time. What I'm kind of able to summarize from all of the discussion is perhaps it's a nice idea to start developing a method in how to analyze, because the standards will ask you to analyze and review. The standards have not prescribed a methodology, so we are free to do that. And then there is another point that I think it's more important to find out about failures in interaction between the components. Regardless if the component was developed extremely complex or not, we can discuss about it. The component in itself has its own architecture to be able to analyze. Otherwise, we should find out another way to analyze it.
But
I'll give the last word to Gab and a final statement from you, Igor, in case there's anything to respond. And then I would like to get into the break because we're a little bit over the time. It's a very good and the right discussion, I guess, we take. but let's continue afterwards in the break as well. So first gap, then Igor
So,
wants to comment.
now, what I want to say is that the safety standard, and I'm talking specifically about ISO 26262, already started to move, take modification to cope with complex software components. Like we started with PAS 8926. Now with the third edition, we are discussing, the addition of reliability data that goes back also, I guess, to the presentation that Akan gave, right? Basically retrieving ops data from the field, right? And use it in the safety case as, as an additional evidence, of stability. Because indeed, it's clear that when we talk about complex software components, the first step to do is to do a partitioning to, an acceptable complexity trade-off. This is what 8926 is about. And then with respect to this component, we need to analyze the interaction, and then for each of the components, we need to prove, to add evidences to claim that it is up to a certain ASIL level. But to some,
I agree with what you say. I think it is okay also to say that the third edition is considering it. But if we have to deal with this kind of problems, I think what we need to do is we need to recognize that these things are systematic analysis dependent on volumes. There is always an inherent risk. And then there is a question of how much risk somebody would like to put forward and how much risk can somebody digest. And this is the question of effort for the time.
Final words, Igor, anything to add?
Right?
Yeah.
Because I mean, he's making the correctly the point was made, you cannot analyze the complex component down to the deepest level.
Looks like you really don't like brakes, right? You don't like brakes.
No.
You can continue the discussion fully in the break. I just want to give a last statement to Igor that we're not fully running out of schedule.
At least it's causing some emotions, right? Which is good.
Yeah,
I was wondering if this might have been too triggering, but anyway, my point is I see people giving up too easily on trying to fix things for real and then starting to talk about trade-off. But, come on, let's at least try to fight the battle before giving up. So I hope that we can come up with monitors that can solve part of these problems instead of just trying to talk about what are we willing to give up as a compromise.
Mhm.
good last words.
Good luck.
Yes.